My name is Dong-geon Lee, and I will be presenting a paper titled "The Semi-Reward Function: Problems in Reinforcement Learning." So, uh, the presentation will proceed as outlined it, and the initial state of this paper, the primary concern we identified was arise when transferring reinforcement learning agents to the real world. Among these challenges, the two major issues we identified in transferring agents to real world are as follows. The first issue is designing rewards used for training agents. Designing a sophisticated reward as in a real world is very difficult or requires significant human efforts. This is one of the factors that makes it challenging to apply agent trained in simulations to real world. So it is the challenging to applying agents that is trained in the simulations to the real world applications. So, and the another issue is that in the current reinforcement learning environment that was structured in the computer code, the all agents are trained to achieve the same goal. In the diverse goal-oriented real world, using such agents necessitates in inefficient methods such as retraining the agent from the scratch for each new goal. And therefore, this paper proposes a reward function systems different from the existing reward function framework. We aim to create a system of agents that can run under the new reward function framework and verify their effectiveness. First, we define a system that can reduce the engineering efforts required for the reward functions in existing reinforcement learning framework. So this is the difference between the classical reinforcement learning and our proposal model. The most significant difference from the classical reinforcement learning lies in the reward function itself. This reward function encompasses both the unified goals and that the agent to reach, and the penalties imposed when the goals are not met. When approaching the theoretical definition, the key difference in the designing these agents compared to the classical agent was that each agent generated from independent attempts would have its own unique goals and be trained accordingly. Therefore, the goal that exists in the classical yield function is embedded within the agent itself. Subsequently, the environment during the agent's training process does not have any information about the which specific goal that each agent to go to reach. Thus, the reward function in this environment is composed only of the information about the action that should not be taken by the agent in that environment. Since this pertains only to the penalty aspect of the classical reinforcement learning, the reward function in this environment consists only half of the information of the original reward function in the classical reinforcement learning. And this is resulting in what we call semi-reward function problems. Um, the closest approach to this in real world is learning how to the driving in the road. When we learn to the drive, not everyone drives toward the same goal, but we combine and learn the information about how to progress toward our own goals and the actions that should not be taken in the road. And this allowing us to reach our individual objectives. So to train this agent, we decide to use the environment, the mini grid. And this environment includes various sub-environments and can create diverse objects such as keys, doors, boas and lavas, etc. It allows the agent to be trained and evaluated on their ability to perform different tasks. Specifically, we choose this environment for the following reasons. The first, the mini-grid has the flexibility to generate a variety of objects, and making it easier to assign a different goals to each agent. Additionally, even if tasks or missions are changing, the information regarding the environment regulation or penalties remain, remains the same, and is making easier to maintain information about the penalties that is given to the agents. And finally, it provides clear information about the partial observations, and this is allowing us to understand the basis on that each agent makes progress in at their own training episodes. And we design an agent of learning through the semi-ordered function as shown. We decide the agent needed to perform two roles. The first role is it has to understand its own goals, which is assigned to their own independent training episode. And second, it needed to decide the action or predict the actions to move toward its own goals based on the interpreted goal informations and its current observations. To achieve this, we created an agent by adopting a transformer structure, which is capable of processing separate inputs. In this picture, the agent Y score and the observation embedding, the output of the observation embedding, they are the different inputs at the same times. And the transformer structure are making easier to handling images or stopper for the processing a long sequence of episodes. So the encoder part was designed to the interpretation of the agent file code, while the decoder part was responsible for the deciding which action to take at the observations. And we added embedding vector to convert observation into input. This is the 2D image or 3D image observations into 1D vector input, and the action encoding part to convert the neural net-based decoder output into a single vector representing for the actions. And we construct agent contain all these parts, and we call this agent as a tutorial-based agent because it's aimed to performing across different goals based on the limited information. And we saw this like some tutorial, and the learning process was divided into two stages, the episode and training stages. To support this, we created a replay buffer to store observations, actions, and other information all occurred during the episodes. And during the episode, the agent performed action based on the current frozen parameters. And during the training stage, it generated laws and updated parameters based on the stored information. And the detailed information about the training method will be explained later. So the process can be expressed like algorithm is as following, and it consists of two stages, the episode stage and the training stage, and there are some steps to store the some informations and to take this information and update the parameters in the algorithm. And the utilized semi-Lie function in the experiment is illustrated in the diagram. This includes both agent-wise goal and the semi-Lie function, and it can be represented similarly to the classical reinforcement learning reward functions. However, in this diagram, the part corresponding to the negative reward is the left part of the diagram, performs the role of the semi-reward function. The other parts of represented are the agent-wise goal, where the agent receives the reward and conclude the episode upon determining itself that it has achieved its own goals. And when configuring the agent with the transformer structure, the main construction and the main consideration was the training method. This is connected to the problem definition because the environment does not include unified goal information, and therefore we could not predefine and generate label information. However, the neural net-based training method created rules by comparing the truth label value with and the agent predicted values, and use this information to update the parameters. In other words, to train the agent, we need to generate loss information. However, since each agent score is different, we could not create uniform loss information in beforehand. At this point, we thought of using the output of the reward function as a loss, considering the reward information as an evaluation of the agent series of the actions within an episode. However, due to the nature of the reinforcement learning, loss is not generated at every action step, but at the end of the episode. And therefore, we decide to the process into the two stages, the episode stage and training stage, like offline reinforcement learning, then generating the loss after the episode stage. At this point, if we input the observation and goal information from when the action was generated into the buffer, we could recalculate the parameters at the time of the action was predicted. Since the parameters were frozen in the episode stage, and the agents are predicted the actions based on the observations and their own goals. Additionally, we did not use any random action selection from the classical reinforcement learning when creating the agents is based on the transformer. This is because during the agent uh, training process, predicting action and updating the parameters consecutively, and it and the parameters are updated very slowly, but selecting random actions, regardless of the parameters, would train the agent based on incorrect information. So we did not use any random action selections. And we also use a distinct loss function as in classical uh, machine learning or deep learning. It is usually line symmetry formed, but we used a variety loss functions in a point symmetry loss function because we believe the goal reward and the penalty information should be reflected as separated losses. Thus, we created various loss functions with point symmetry and used one of the most stable performance. From this picture is the one of the sub-environments lizard, and we use the cube of the episode reward is the uh, bottom of the middle graph. And the objective of our experiment was as follows. First, we aim to demonstrate that the structure we designed, including the semi-Liouville function and tutorial-based agent, is effective for training reinforcement learning agents. And additionally, we want to see if an agent trained in a specific environment could maintain its performance when transferred to different environments using the limited information from the initial environment. The main difference in the experiment environment was the modification of the reward function. So we modified the reward function from classical reward function to semi-reward function. To achieve this, we defined an action, such as attempting to execute a forward action while facing a wall, as regulated actions in the environment, and generated a semi-reward function accordingly. And the hyperparameter used in the experiment are listed below, and the explanation for each parameter has been provided. You can find these details in the appendix of the paper. And finally, we will present the result of the experiment. And here is how to read the table. In the leftmost column of all tables are information about the environment in which the agent was trained is provided. And conversely, the top row are the provided environment in which the trained agent was evaluated. And the name about the environment, such as in this diagram, the empty is the name of the sub-environment. So this is like agent-wise goals that agent have to achieve in the train or evaluation sub-environment. So, all evaluations are presented as the average and the STD of the reward obtained by the agent over 10 runs in the evaluation environment. And thus, for all models, an average reward close to 1 indicates that the agent performed well in that environment, and the lower STD suggests that the agent constantly reach the goal in consecutive runs. And note that to maintain some consistency with the original environment, we did not change the reward function of the existing environment. And I said the classical environment, and therefore the reward range for the environment evaluated with PPO agent is the range 0 to 1, while the environment evaluated the hours model is ranged from -1 to 1. So there are some different ranges from classical model and hours model. This is the first experiment and involves testing in the environments of the same task, but with the different size. In the case of the PPO, it's the classical reinforcement learning method, which can be considered yeah, this is the classical training method, and the PPO agent shows very good performance in the environment in which it was trained on. However, the performance drops when the environment size is the larger, than the training environment. In contrast, our model shows slightly lower performance in the environment in which it was trained on compared to the PPO, but it maintains its performance when transferred to the environments of the different sizes. And it consistently performs well even in the larger size of the environment. And the following result is about the with the same mission. Uh, sorry, it's the different mission and different size from the training environment, and we can observe similar results to the previous experiment. And we want to note that in particular, our model demonstrates very high performance in the larger size of the environment, and the other factors are explained the later experiment result. And finally, we present the result of the evaluating agent training in more complex environments across the various sub-environments. The table showed that while the PPO agent failed to perform in all environments except for it was trained, but our model can operate even in the other sub-environments. In this context, rather than interpreting these results that our model are superior to the PPO models, but we suggest that the PPO is the being based on a promise-based agent is more effective in the environment with uniform goals. However, it struggles with tasks requiring the agent to pursue different goals. But our models, on the other hand, appears more suitable model for different goal tasks. And therefore, we were able to develop a model that using semi-reward function and the tutorial-based agent is less sophisticated designing than the classical reward function, but more appropriate for the training agent that pursue different goals. Uh, Nevertheless, our model does have some limitations, including instability during the training stage, and challenges in handling the agent-wise goals that is changing in the training stage, and the variability in learning outcomes depending on the maximum number of the step is the limitation of these systems. And this is and for my presentation, and thank